Well, our next subject is to learn how to treat non-ideal reactors with the tools that are available to us. The tools that are available to us are the treatments that we can perform with the ideal reactors. And also, we have learned a tool that will give us the behavior of the black box reactor in terms of the residence time distribution of an inert tracer. So using the residence time distribution of the inert tracer, we can at least guess what type of behavior we might have in a non-ideal reactor. So let us have a dotted frame around a non-ideal CSTR, right? That will represent the black box behavior. Let us have our inert tracer experiment, injecting the inert tracer, and let us monitor the product. But this time, we will know what we are getting and why we are getting that. Now in this non-ideal CSTR, which is relatively large in comparison to the typical CSTRs that I was drawing, that we might have the dead zones, that the impeller is not sufficiently large to mix the contents at the corners of the reactor. And instead of a flat boundary, our impeller also exhibits a vortex, and this vortex results in the bypassing of some of the fluid without even mixing with the rest of the contents. As a result, we have in part of the reactor a perfect CSTR behavior that our inert tracer will go through an exponential decay. In part of the reactor, we are going to have domains that interact with the rest of the reactor only through molecular motions. By the molecules diffusing in and out of this domain, they are the dead zones. We are going to have bypass domains which will behave like a plug flow reactor. And the probability, the density function, and the washout curve will look like this. So we're going to have a relatively small fraction of this as a CSTR performance. We're going to have a very, very long tail for a dead zone. And then we are going to have a bypass, a sharp bypass which behaves like a plug flow reactor. So add them up, this plus this plus this, our function should look like this. So it is the experience of the engineer that is going to dissect the components into a CSTR, a dead zone, and a bypass zone. But one good aspect of the tracer analysis is the area under these curves are going to be proportional to the volumes. Let me call this A1. Let me call this A2. And let me call this A3. A1 plus A2 plus A3 is going to be proportional to the volume of this reactor, the volume of the contents, and their relative proportions are going to be representative of the fraction of the fluid that is undergoing the changes as dictated by the residence time distributions. The problem with the residence time distribution analysis is that it is not going to allow us to determine which is happening first, which is happening after. Now, imagine that you have a plug flow reactor and a CSTR. In series. In the first situation where we have the plug flow reactor as the first unit, in the second situation, we have the CSTR as the first process unit. When we introduce the inert tracer, here or here, both of these situations will give rise to the same residence time distribution curve. That we are going to have a delay that is going to correspond to the plug flow reactor. It doesn't matter whether the plug flow reactor is before or after the CSTR. Then immediately after, we have the CSTR behavior. We know that we have one plug flow reactor with a space-time of tau1 and the CSTR with a space-time of tau2 dictated by the decay exponential decay. We can identify tau1 and tau2, but we cannot tell whether the plug flow reactor is in front of or before or after the CSTR. This is the problem with the residence time distribution analysis. But once we have the residence time distribution analysis, we can estimate the performance of the reactor, whether we have a plug flow reactor, a CSTR. By making tests and trials, we can identify whether our non-ideal reactor, how is it best represented? What type of reactor configuration represents our reactor best? So this is the simplest approach that we analyze a typical real non-ideal reactor.